Integral calculus, a system for integration. One of the problems many students have in integrating is deciding which method to use for a particular integral. So here is a system of questions which you can ask yourself in order to do integration. So here are, first of all we say, is it a standard integral? Now all of these are standard integrals. These last two perhaps a bit of an adjustment of a standard integral, but pretty much standard as well because we can recognize them straight off. So if it's yes, we go ahead and integrate. First one here, well, that is just a polynomial. Integral of a polynomial, straightforward, don't forget the plus c. Sec squared x, well, sec squared is the derivative of tan, so therefore tan of x plus c, there we are. 1 over x is the derivative of ln, so 4 over x. If we see this as 4 times the integral of 1 over x, then we end up with 4 ln x plus c. Cot x cosec x, well, this is nearly the derivative of cosec x. The only difference is the derivative of cosec x has a negative. So there we have a negative on the outside to allow for that, and now we have exactly the derivative of cosec x, so therefore it becomes that negative cosec x plus c. Cos x is a standard integral, as is sin x. Well, this is cos squared, but it's pretty standard because we need to remember something, and that is that the way we integrate cos squared or sin squared is that we express cos squared or sin squared as a function of cos 2x, the double angle formula. So there's the double angle formula we would use for cos squared x there, and we solve that to give cos squared x. It'll be half brackets cos 2x plus 1. So therefore the integral is half integral brackets cos 2x plus 1 dx. Now the integral of cos 2x is half sin 2x. With that half gives it a quarter, and the integral of half x is half x, and plus the c. This here, we'll call it standard because it's in a particular very recognizable shape. Sin cos, sin cos, or cos cos are three pretty much recognizable shapes. This one here we know we write as a combination of the couple of compound angle formulae. So we say, well, which ones give you sin cos? It's the sine expansions. So there we are, sin 3x plus 5x, sin 3x minus 5x. If we expand them and add them, the second term in each is eliminated, and we end up twice the first term, which is that. So we are going to write it as that. There we are. And in fact, there is a formula for that, often on a formula sheet, so you may not even have to go through the procedure. So there it is. We can separate out the integral, two separate integrals, and then we just straightforward, pretty standard integrals. If not a standard integral, we look and say, well, is it a product? If it's yes, well, is it a function multiplied by its derivative times a constant if necessary? Is this a function multiplied by its derivative? Well, have a look here. There's sin x, there's the derivative, cos x. So the answer is yes in this case. So we can either use inspection or substitution. We can let u equal sin x and go from there, or we can just do it by inspection. I'm going to do it by inspection. To differentiate to get sin x, I must have had sin squared x, and there's the cos x coming out because of the derivative of the inside function in chain rule. So there we are. If we differentiate that, 2 sin x times derivative of the inside, which is cos x, so it becomes 2 cos x sin x, plus c, and the c would differentiate to give you 0. If not, is it perhaps the product of a function of something times the derivative of that something? If you consider here, this first one, that's the square root of, and then inside we have x cubed minus 4, and there's the derivative of x cubed minus 4. If you look at this one here, there we have sine of x squared, and there is the derivative of x squared. Well, with a k, because that's half the derivative of x squared. But that's fine. So we're going to do those. Yes, and we'll use substitution or inspection, but often substitution's better. So in the first case, we're going to let u equal x cubed minus 4. Now this is just the pattern. Du by dx equals 3x squared. Du equals 3x squared plus x. So we can now write this with 3x squared plus x dx there. And it's the same thing. Now we can just substitute u for x cubed minus 4 and du for 3x squared dx. There it is. Integrate and then substitute back. This case as well, we're going to let u equal x squared. Derivative of du by dx is 2x, which means du is 2x dx. So I'm going to write this as 2x dx. Because I'm writing it as 2x dx, I need a half there. So now I can substitute half integral of sine of u du. There it is. Integrate. Substitute back your x squared for u. If no, is it a product involving trig or other functions? This actually is still yes, really, because it could be there as well. It could be, but let's have a look at it in terms of this one, the trig ones. Square root of 1 minus cos x, and that is the derivative of 1 minus cos x. So therefore, yes, substitution. So we're going to let u equal 1 minus cos x, du by dx, sin x, du, sin x dx. So I'm going to take that sin x for that dx, write it there, and there's what's left. I can now substitute the u, and I'll have square root of u, or u to the half, du. Integrate and substitute back. No? Well, let's try integration by parts. So if we have x times sine of x, I can see that x is not the derivative of the inside function. In this case, I can see that x squared is not the derivative of the inside function. But what I can do is recognize it as two functions multiplying together. Now, remember, with parts, we need to say, well, one is a function and the other one is already a derivative. So let's take this one here. I'm going to let that be the function and that be already the derivative. So therefore, if I want uv, I have to integrate it. I get minus cos x minus integral of v, well, there's du is derivative of x, and v once again minus cos x. So it becomes plus integral of cos x, and integral of cos x is sin x. So there we are. In this case, we'll take that as the function v, which is already dv, and that as the u. I don't want to make this the dv, because then I'd have to integrate it, and I just cannot integrate it at the moment. But I can integrate that and differentiate that. So there is your integration by parts. Right, if not those, is it perhaps a fraction? And if it's yes, well, is it similar to the product here? Is it perhaps something like that? Well, if you have a look here, we see a fraction. So first thing I'll always ask myself is this either this derivative or a product of a constant with the derivative of this? Well, yes, it is. Derivative of this is 2x minus 2. That's half of 2x minus 2. So therefore I can do that. So let's use inspection or substitution. In this case I'll do substitution to make it clearer. So u equals that, du by dx. Du equals 2x minus 2 dx. Now I only have x minus 1 dx, so I'm going to say 2x minus 2 and introduce a half on the outside. So there's your du, and there's 1 over u. Now, of course, the integral of 1 over u becomes ln of u. And strictly speaking, we should put it in absolute value because we cannot have ln of a negative. Substitute back that value, and there is our integral. If no, could it be similar to this one, where this one's similar to that one, and this one's similar to this one? So now, remember here, I just had x over x squared minus 2x minus 2. In this case now, I have the square root of x squared minus x minus 2. But when I look at this, I say, well, the derivative of x squared minus x minus 2 is 2x minus 1. So yes, this here is your f prime of x, where that's the f of x. So I'm going to do a u substitution as well. Yes, I'm going to substitute. I'm going to have u equal to x squared minus x minus 2. There we are. That means du by dx. Therefore du 2x minus 1 dx. Well, that's useful. 2x minus 1 dx, so I have it aside. And I have that to the minus half. Since u is equal to that, I'll end up with u to the minus half. And I can just integrate it as I would any polynomial. Add 1 on and divide by the result. And I get the 2 there by dividing by half. Then we substitute back. Well, is it a polynomial less than or equal to 1, degree less than or equal to 1, and a polynomial of degree equal to 1? If yes, we could do switch around. I don't know if you remember switch around or if you've done it, but that's very useful. But it really only is useful if it's of degree 1 there. I could use substitution here. I could let u equal that x minus 2 with the aim of ending up with a monomial below, which means I need to work out what 2x plus 1 will be. So if u is x minus 2, then x is u plus 2. 2x plus 1 will be twice u plus 2 plus 1, 2u plus 5. So that's going to become u, and that's going to become 2u plus 5. Let's do our bits for the substitution. Du by dx, well, that's 1, so therefore du is equal to dx. So this here, there, that can become du. That's your 2u plus 5, and that is your u. Separate it into two separate terms now, and we integrate each separately. Remembering, this is 5 over u, so it's 5 ln u, and it's absolute value of u. And here we go, here we've substituted back. Now notice here that this is 2x when u was x minus 2. Well, all I've done is I've said, well, twice u will be 2x minus 4. Why don't we just take that minus 4 and say combine it with the c1, and that gives us a new constant. That's why we don't need a numeric constant here and then another variable constant there. Is it perhaps partial fractions? If it's a fraction, is it perhaps partial fractions? And usually partial fractions works if you can factorize the denominator. So here's a case. I can make that into two fractions with x plus 3, x minus 2 as your denominators. Finding a common denominator and equating just the numerators, 2x minus 1. We're going through this quite fast, but this is not teaching in the sections. It's just reminding you and giving you a system. Equals, and there's numerator. Substitute minus 3 to get rid of the b, and we end up with a equal to 7 over 5. Substitute 2 to get rid of the a, and we end up with b equals 3/5. So we could therefore write this as this here. Sorry, that a and that b should not be there.